Welcome to the deep dive. Ready to connect some maybe unexpected dots today?
Definitely. We're jumping into a really interesting mix.
Yeah, we're looking at how pretty abstract mathematics, specifically integration, can actually become a tool for something very real world,
Hmm.
tackling environmental waste.
It was a great example, isn't it? Theory hitting practice.
So our source material gets right into this application.
It does. It focuses on how integral calculus gives us a method to estimate packaging waste, and specifically for processed agricultural commodity.
Okay, right. Process agricultural commodities. So let's unpack that a bit. Our mission here is to figure out how this math tool integration can be used to estimate waste from things like, well, bagged flour, canned vegetables.
Exactly. Packaged sugar, all those staples, the kinds of products that move in absolutely massive volumes.
And this specific type of waste, it's a big challenge, right?
Yeah.
Why is that, and how does integration even begin to offer a solution?
Well, that's the key question, really. Packaging waste from these processed goods is just a huge, huge contributor to landfills, environmental strain
Yeah.
globally.
Yeah.
And because these things are produced, distributed, often in such enormous quantities, right,
Hmm.
across these really complex supply chains,
Uh-huh.
getting an exact count of every piece of packaging waste at every single step, from the factory line right to your kitchen bin,
Right.
it's virtually impossible.
Right. Too complex.
You need a systematic way to estimate the total scale. You just can't count it all.
And that's where the math comes in. That's where integration fits. Now, we're not explaining Calculus 101 here. Obviously, our listeners get that integration is about summing things up. But how does that summing apply to, trash?
Okay, think about waste generation. Don't think of it as just one fixed number, but as a continuous process. It might vary over time, maybe across different places in the supply chain.
Right, like different stages.
Exactly. Different stages, initial packaging, transport, retail, consumption waste gets generated at different rates. Maybe faster here, slower there.
Hmm.
Integration lets you model that, lets you sum up all those small, maybe variable rates of waste generation over the whole process or the whole chain.
Ah, okay.
And that gets you to a total estimated quantity.
So instead of like trying to count every single discarded box or wrapper,
Yep.
which you said is impossible,
Yeah.
you could maybe develop a function,
Right.
something that describes the rate waste is being made, like waste per ton of product or waste per mile it travels.
Precisely. Or maybe waste per hour of processing time, things like that.
Okay.
And then you use integration to calculate the total waste that accumulates over a whole production run, say, or transport route, or even an entire year of operation.
That makes sense. You could potentially use real data, right? Production volumes, transport distances, maybe even consumption patterns to build that rate function.
Absolutely. You'd want to inform that function with the best data you have. Integration then
Sure.
just provides the mathematical engine, to calculate the area under the curve.
Right, the classic calculus concept.
Yeah, where the curve is just representing that rate of waste generation over whatever you're measuring against time, volume, distance, whatever
Yeah.
it is. And that area gives you a number, a quantifiable estimate of the total packaging waste for those processed goods.
This is where it gets really practical, I think. It takes this concept you might just see in a math class
Mhm.
and gives it direct practical use in environmental accounting, logistics, corporate sustainability reporting, things like that.
Okay.
Because getting that number, that quantifiable baseline estimate for processed agricultural packaging waste, that seems absolutely essential for businesses, maybe policymakers too.
But definitely, to set meaningful targets for reduction, you first need to know what you're dealing with.
Right. Or to justify spending on better packaging or maybe designing more efficient recycling programs. You need the numbers.
It really highlights a broader point that our source material touches on. These complex real-world challenges, they often need tools from places you might not expect. Estimating waste at scale using integration is just one specific application, but it's for a critical environmental problem. It shows these mathematical concepts aren't just theory. They are powerful instruments for actually measuring and understanding the physical world.
So wrapping this up then, what does this all mean for you listening? We've basically seen how mathematical integration gives us a concrete way to move past just guessing.
Yeah, to actually estimate the large-scale packaging waste from all those processed agricultural products.
And understanding the scale of any problem, that's always the crucial first step, isn't it? Before you can effectively tackle it.
Absolutely. And math, in this case integration, provides a powerful tool for doing that essential estimation.
So maybe a final thought to leave you with. Think about all the other complex real-world problems out there. Environmental, economic, social ones. How many of them might have solutions or at least critical insights kind of hidden within seemingly abstract mathematical or scientific concepts that we just haven't connected yet? What other, unlikely tools might be waiting to help us understand and maybe even solve some of those big challenges?